Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. The lighthouse stars that spin incredibly fast. In 1967, a graduate student named Jocelyn Bell noticed something peculiar in her radio telescope data, a signal that pulsed with extraordinary regularity, repeating every 1.3373 seconds. The precision was so remarkable that she and her advisor initially wondered whether they had detected an artificial signal from an extraterrestrial civilization. They jokingly called it LGM-1 for Little Green Men. But as more of these pulsing sources were discovered, each with its own precise period, it became clear they were witnessing something natural, but entirely unexpected. Rapidly spinning neutron stars whose beams of radiation sweep across Earth like cosmic lighthouses. These objects, now called pulsars, are among the most extreme objects in the universe. They are neutron stars, the collapsed cores of massive stars that exploded as supernova, compressed to densities where a sugar cube-sized amount of material would weigh as much as a mountain. What makes pulsars special is not just their incredible density, but their rotation. These stars spin at rates that seem impossible for something so massive. Many complete one rotation in less than a second, some in mere milliseconds, whirling around hundreds of times per second while containing more mass than the Sun. The story of a pulsar begins with the death of a massive star. When a star, at least 8 times more massive than the Sun, exhausts its nuclear fuel, its core collapses catastrophically. The outer layers rebound and explode outward as a supernova, but the core continues collapsing until nuclear forces halt the compression, creating a neutron star about 12 miles across. This neutron star inherits the angular momentum of the original star's core, but because the radius has shrunk by a factor of perhaps 100,000, the rotation rate increases dramatically through conservation of angular momentum. Imagine a figure skater pulling their arms inward during a spin, rotating faster and faster as their radius decreases. The collapsing stellar core undergoes the same process, but on a far more extreme scale. A star that was rotating once every few weeks might produce a neutron star that rotates several times per second. The fastest spinning pulsar known, designated PSRJ 1748-2446 AD, rotates 716 times per second. At its equator, the surface is moving at approximately 70,000 miles per second, nearly 1/4 the speed of light. At these speeds, the neutron star is ablate, bulging significantly at its equator due to centrifugal forces, yet it holds together through the tremendous strength of neutron degenerate matter and its own crushing gravity. The lighthouse effect that makes pulsars detectable comes from their magnetic fields. Neutron stars possess the strongest magnetic fields known in the universe, typically 1 trillion times stronger than Earth's magnetic field. When the core of the parent star collapses, any magnetic field present is compressed and amplified tremendously. This field doesn't simply shrink, it gets concentrated into a much smaller volume, intensifying to values that would tear apart atoms and polarize the vacuum of space itself. This intense magnetic field is not aligned with the neutron star's rotation axis. Just as Earth's magnetic poles don't coincide with its geographic poles, a neutron star's magnetic axis is typically tilted relative to its spin axis. Charged particles, primarily electrons and positrons, are accelerated along the magnetic field lines, particularly near the magnetic poles. These particles, accelerating at relativistic speeds, emit intense beams of radiation through a process called synchrotron radiation. The beams emerge from the magnetic poles, creating two searchlights that sweep through space as the neutron star rotates. When one of these beams sweeps across Earth, we detect a pulse of radio waves, X-rays, or gamma rays, depending on the pulsar's characteristics. The pulse arrives with extraordinary regularity. The best pulsars keep time as accurately as atomic clocks, varying by only microseconds over years. This precision exists because the neutron star is such a stable rotator. Its enormous rotational inertia, combined with its extreme density and rigidity, means that nothing can easily change its spin rate. It's like an enormous cosmic flywheel, storing vast amounts of rotational energy and releasing it only very gradually. The radio emission mechanism is complex and still not completely understood, despite decades of study. The acceleration of charged particles near the magnetic poles creates a cascade of electromagnetic radiation. These particles follow the curved magnetic field lines, and as they accelerate, they emit photons. These photons can interact with the intense magnetic field to create more particle-antiparticle pairs, which then accelerate and create more photons, building up a cascade that produces the intense radio emission we detect. The region where this occurs, just above the magnetic poles, is called the polar cap, and it's here that the lighthouse beams originate. Not all pulsars emit at the same wavelengths. Some are primarily radio pulsars, detected through their radio emission. Others are X-ray pulsars, emitting primarily high-energy X-rays. A few emit gamma rays, the most energetic form of electromagnetic radiation. Some pulsars emit across the entire electromagnetic spectrum simultaneously, creating pulses detectable from radio waves through gamma rays. The emission properties depend on factors like the neutron star's age, its magnetic field strength, its rotation rate, and the environment surrounding it. Young pulsars, recently formed in supernova explosions, tend to rotate faster and have stronger magnetic fields than old pulsars. The Crab pulsar, formed in a supernova observed by Chinese astronomers in 1054 AD, rotates 30 times per second and emits powerfully across the electromagnetic spectrum. It sits at the center of the Crab Nebula, the expanding remnant of that supernova explosion, and its intense radiation illuminates the surrounding nebula, causing it to glow. The pulsar acts like a cosmic power station, converting its rotational energy into electromagnetic radiation and high-energy particles that energize the nebula. Pulsars slow down over time, gradually losing rotational energy. This spin-down occurs because the rotating magnetic field acts like a brake. The magnetic field lines extend far into space, and as they rotate with the neutron star, they drag charged particles along, accelerating them and carrying away energy and angular momentum. This magnetic braking gradually robs the neutron star of its rotational energy. A young pulsar might slow down measurably over just a few years, while an old pulsar might take millions of years to show detectable changes in its period. The rate at which a pulsar slows down reveals information about its magnetic field strength and age. By measuring the current rotation period and the rate of change of that period, astronomers can estimate how long the pulsar has been spinning down and how much longer it will continue to pulse before its rotation becomes too slow and its magnetic field too weak to generate detectable radiation. Most pulsars have lifetimes of tens of millions of years as active radio sources before they fade from detectability, though the neutron star itself continues existing and spinning, just no longer producing observable pulses. Some pulsars experience sudden speed-ups, called glitches. The neutron star's rotation rate, which normally decreases steadily, suddenly increases slightly, then resumes its gradual slowdown. These glitches are thought to occur because the neutron star's interior contains a superfluid, a state of matter with zero viscosity that can flow without any resistance. This superfluid rotates faster than the star's crust and occasionally angular momentum transfers suddenly from the superfluid to the crust, causing the observable spin-up. Glitches provide rare windows into the exotic physics occurring inside neutron stars, where matter exists in states impossible to recreate in laboratories. Millisecond pulsars present a fascinating puzzle. These pulsars rotate hundreds of times per second, far faster than young pulsars, yet they're old neutron stars, billions of years old. How can an old pulsar be spinning so fast? The answer lies in a process called recycling. A millisecond pulsar was once a normal pulsar that slowed down over hundreds of millions of years. But if it's in a binary system with a companion star, and that companion evolves to become a giant star, matter can flow from the companion onto the neutron star. This infalling matter carries angular momentum, spinning up the neutron star like water hitting a water wheel. Over millions of years, the neutron star is spun up to millisecond periods, recycled into a new youth of rapid rotation. Some pulsars are part of binary systems where we can directly observe this process happening. X-ray binary pulsars show X-ray pulses as the neutron star accretes material from its companion. The infalling material, heated to millions of degrees before hitting the neutron star's surface, emits intense X-rays. These systems are the evolutionary precursors to millisecond pulsars, caught in the act of being spun up by accretion. The most rapidly rotating pulsars ever discovered are all millisecond pulsars, and some of them are in dense globular clusters where stars are packed closely together. The high stellar density in these clusters makes binary interactions more likely, creating environments where many neutron stars can be recycled through accretion. Some globular clusters contain dozens of millisecond pulsars, creating a cosmic percussion section where numerous neutron stars pulse at different rates, each one a precisely ticking clock with its own unique period. Pulsars can also have planets. The first exoplanets ever discovered orbit a pulsar called PSRB 1257+12. These planets were detected through tiny variations in the pulsar's timing. As the planets orbit, their gravity tugs the pulsar slightly back and forth, causing the pulses to arrive slightly early or late in a periodic pattern. The planets orbiting this pulsar are thought to be second-generation worlds, formed from the debris of the supernova explosion that created the neutron star, or possibly from material that later fell back onto the system. These are harsh worlds, bathed in intense radiation from the pulsar, utterly unlike the planets orbiting normal stars. Binary pulsars, where two neutron stars orbit each other, provide extraordinary laboratories for testing general relativity. The orbital motion of such systems produces gravitational waves that carry away energy, causing the orbit to shrink over time. The rate of orbital decay matches Einstein's predictions with incredible precision. The first binary pulsar discovered, PSRB 1913+16, provided the first indirect evidence for gravitational waves. Decades before, gravitational wave detectors directly observed them from merging black holes and neutron stars. The regularity of pulsar timing has practical applications. Astronomers use networks of millisecond pulsars across the galaxy as a cosmic timing array, watching for tiny correlated deviations in their pulse arrival times that would indicate gravitational waves passing through the galaxy. These pulsar timing arrays are sensitive to gravitational waves with much longer wavelengths than ground-based detectors can observe, potentially detecting the gravitational wave background from supermassive black hole mergers throughout the universe. Pulsars also serve as natural laboratories for extreme physics. The conditions near their surfaces, intense magnetic fields, extreme gravity, densities exceeding that of atomic nuclei, cannot be reproduced on Earth. By observing pulsars across the electromagnetic spectrum and measuring their properties precisely, physicists learn about how matter behaves under conditions that push the boundaries of our physical theories. Testing general relativity in strong gravitational fields and probing the equation of state of matter at nuclear densities. These spinning neutron stars, these cosmic lighthouses flashing their beams across the universe, represent one endpoint of stellar evolution. From the violent collapse of a massive star's core emerges an object so dense, so rapidly spinning, so strongly magnetized that it challenges our understanding of physics. Each pulse detected from a pulsar is a message from one of the universe's most extreme environments, a precisely timed signal carrying information about physics at the edge of what's possible, reminding us that the universe contains objects and phenomena far stranger than we could have imagined before we discovered these remarkable, spinning stellar remnants. The zone where life could exist. Life as we know it requires certain conditions to exist. Too hot, and water boils away. Too cold, and water freezes solid. Without liquid water, life as we understand it cannot survive, at least not the kind of carbon-based, water-dependent life that evolved on Earth. This simple requirement creates a critical region around every star called the habitable zone, sometimes nicknamed the Goldilocks zone, because conditions there are neither too hot nor too cold, but just right for liquid water to exist on a planet's surface. Understanding this zone and what makes it special reveals both the requirements for life and the astonishing variety of places in the universe where life might possibly emerge. The habitable zone is not a single precise distance from a star, but rather a range of distances, a band extending outward from the star where temperatures allow water to remain liquid. For our Sun, this zone extends roughly from about 90 million kilometers to about 150 million kilometers from the Sun. Earth, orbiting at about 150 million kilometers, sits comfortably within this zone, though closer to the inner edge than the middle. Venus, at about 108 million kilometers, orbits just inside the inner edge, where temperatures are too high. Its surface temperature exceeds 450 degrees Celsius, hot enough to melt lead, far too hot for liquid water. Mars, at about 230 million kilometers, orbits near or just beyond the outer edge, where temperatures are generally too cold. Though liquid water might occasionally exist in certain locations under special conditions. The boundaries of the habitable zone depend entirely on the star's properties. Hotter, brighter stars have habitable zones located farther out because their intense radiation heats planets to higher temperatures. Cooler, dimmer stars have habitable zones located much closer in. A red dwarf star, the most common type of star in the galaxy, might be only 1/10 as luminous as the Sun, meaning its habitable zone would be about 1/3 the distance from the star. A planet orbiting in the habitable zone of a red dwarf might orbit only 10 million kilometers from its star, closer than Mercury orbits our Sun, yet still maintain temperatures suitable for liquid water because the star is so much dimmer. The habitable zone also depends on the planet's atmosphere. A thick atmosphere with greenhouse gases can trap heat and keep a planet warm even if it orbits farther from its star than the outer edge of the simple, habitable zone. Venus demonstrates the opposite effect. Its extremely thick carbon dioxide atmosphere creates a runaway greenhouse effect, trapping heat so efficiently that surface temperatures soar far beyond what you would expect from Venus's distance from the Sun alone. Without this greenhouse effect, Venus might be cool enough for liquid water. With it, the planet is an inferno. Mars provides another instructive example. Mars orbits near the outer edge of the Sun's habitable zone, and its thin atmosphere, less than 1% the pressure of Earth's atmosphere, cannot retain much heat. Surface temperatures average around -60 degrees Celsius, far too cold for liquid water most of the time. But billions of years ago, Mars had a thicker atmosphere and likely had liquid water flowing on its surface, creating the river valleys and lake beds that spacecraft have photographed. Mars lost most of its atmosphere over time, probably because its weak magnetic field couldn't protect the atmosphere from being stripped away by the solar wind. The planet moved out of effective habitability not by changing its orbit, but by losing the atmosphere that kept it warm. Earth maintains liquid water on its surface through a fortunate combination of factors. Our distance from the Sun provides a baseline amount of heating. Our atmosphere, with modest amounts of carbon dioxide and water vapour, acting as greenhouse gases, traps enough heat to raise the surface temperature by about 33 degrees Celsius, above what it would be without an atmosphere. Our magnetic field, generated by the liquid iron core's motion, shields the atmosphere from the solar wind, preventing the atmospheric loss that doomed Mars. Our planet's size gives it enough gravity to hold onto its atmosphere over billions of years. But the habitable zone is more complex than just distance from a star and atmospheric composition. Other factors influence whether life could actually emerge and survive. Planetary mass matters. A planet too small cannot retain an atmosphere because its weak gravity allows atmospheric gases to escape to space. A planet too large might have such a thick atmosphere that surface pressures become extreme, or might retain so much hydrogen and helium from its formation that it becomes more like a miniature gas giant than a terrestrial world. The planet's rotation rate influences habitability as well. A planet that rotates very slowly, or is tidally locked to its star, showing the same face always toward the star as the Moon does to Earth, would have extreme temperature differences between the permanent day side and permanent night side. The day side might be too hot for liquid water, while the night side freezes. Venus rotates extremely slowly, taking more than 200 Earth days to complete one rotation, though its thick atmosphere distributes heat efficiently enough that temperatures are fairly uniform across the planet, despite this slow rotation. Stellar variability affects the habitable zone's stability over time. The Sun's luminosity has increased by about 30% over its lifetime. Early in Earth's history, when the Sun was dimmer, Earth received less heat. Yet geological evidence shows that liquid water existed on Earth's surface going back nearly 4 billion years, despite the fainter Sun. This is called the faint young Sun paradox. The solution probably involves a thicker atmosphere with more greenhouse gases in Earth's past, compensating for the dimmer Sun and keeping temperatures warm enough for liquid water. As stars age, their habitable zones move outward. The Sun will continue brightening over the next billion years or so. Eventually, perhaps in 1 billion to 1.5 billion years, the Sun will become bright enough that even with our current atmosphere, Earth's surface will become too hot for liquid water. The oceans will evaporate, water vapour will accumulate in the atmosphere, and the increased greenhouse effect will push temperatures even higher in a runaway process. Earth will exit the habitable zone, not because Earth moves, but because the habitable zone moves outward as the Sun brightens. Subsurface habitability expands the possibilities beyond the traditional habitable zone. Moons orbiting gas giant planets can have liquid water beneath their icy surfaces, even if they orbit well outside the star's habitable zone. Jupiter's moon, Europa, and Saturn's moon, Enceladus, both have subsurface oceans kept liquid by tidal heating, the gravitational squeezing from their parent planets that generates internal heat. These moons demonstrate that life might not require surface liquid water or even a planet within the traditional habitable zone. The requirements might simply be liquid water somewhere, an energy source, and the right chemical ingredients. Tidal heating expands the possible locations for life significantly. A planet or moon doesn't need to orbit at a specific distance from its star if internal heat from tidal forces can keep subsurface water liquid. This might be particularly important for moons orbiting planets in the habitable zones of red dwarf stars, where tidal locking to the star might make surface habitability challenging, but subsurface oceans remain possible. The chemical composition of the planet matters as much as its location. Life requires more than just water. It needs raw materials, Carbon, nitrogen, phosphorus, sulfur, and trace amounts of many other elements are essential for the biochemistry we know. Planets that form too close to their star might lack volatile elements like carbon and nitrogen that are essential for life. Planets that form too far out and then migrate inward might have compositions dominated by ices, rather than having the right balance of rock, metal, water, and organics. Stellar type influences habitability in ways beyond just temperature. Red dwarf stars, while having habitable zones close in, pose challenges for life. These stars frequently produce powerful flares, sudden bursts of radiation, and charged particles that could strip away planetary atmospheres and damage biological molecules. A planet in the habitable zone of a red dwarf would need a strong magnetic field to protect against this radiation. Additionally, red dwarfs are so dim that their habitable zone planets likely become tidally locked, always showing the same face to the star, which creates the extreme temperature contrast problem. More massive stars, while having habitable zones farther out, present a different problem. They burn through their fuel quickly and don't live long enough for complex life to evolve. A star twice the Sun's mass might only live a few billion years before exhausting its hydrogen fuel and evolving into a red giant. On Earth, simple life emerged fairly quickly, within the first billion years, but complex multicellular life took nearly 3 billion years to appear. More massive stars might not remain stable long enough for complex life to evolve on their planets. Binary star systems where two stars orbit each other create more complicated habitable zones. If the stars orbit close together, planets might orbit far enough from both stars that the pair acts like a single brighter star, creating a habitable zone at a large distance. If the stars are widely separated, planets might orbit just one star in a habitable zone, determined primarily by that star's properties. But intermediate cases, where the stars are separated by distances comparable to their habitable zones, create complex and potentially unstable conditions for planets. The galactic habitable zone adds another layer of consideration. Different regions of the galaxy have different properties relevant to life. Near the galactic center, stars are packed more densely, and supernova explosions occur more frequently, potentially sterilizing planets with intense radiation. Far in the outer reaches of the galaxy, stars might be too poor in heavy elements to form rocky planets with the chemical complexity needed for life. The region where our Sun orbits, about halfway out in the galactic disk, might represent a galactic habitable zone where conditions are most favorable for life to emerge and survive long term. Exoplanet discoveries have found thousands of planets, many within their stars' habitable zones. Proxima Centauri b, orbiting the nearest star to our Sun, sits within its star's habitable zone, though whether it actually has liquid water and a protective atmosphere remains unknown. Kepler and other missions have found dozens of roughly Earth-sized planets in habitable zones, though determining which of these might actually host life requires detailed atmospheric studies that current telescopes can barely begin to perform. The concept of habitability continues evolving as we learn more about the diversity of planetary environments. Life might exist in forms very different from Earth's biology, adapted to environments we would consider extreme. Subsurface oceans beneath ice shells, atmospheres of exotic chemistry on planets very different from Earth, even clouds in the atmospheres of gas giants. All these represent potential habitats that expand the zone where life might exist far beyond the simple band of distance where liquid water exists on a planet's surface. The habitable zone represents our best current understanding of where to look for life, based on the one example we have: Earth. It's a starting point, a place to begin the search, knowing that life's possibilities might extend far beyond this simple definition. The zone where life could exist might be much larger than we imagine, encompassing not just planets at the right distance from their stars, but moons with tidal heating, planets with exotic chemistries, and environments we haven't yet conceived, each one a potential home for biology waiting to be discovered. What intelligent alien technology might reveal. The search for extraterrestrial intelligence has focused primarily on listening for radio signals, deliberate transmissions from alien civilizations trying to communicate across the cosmos. Since 1960, when astronomer Frank Drake conducted the first systematic search for alien radio signals in what came to be called Project Ozma, scientists have scanned the sky with increasingly sensitive radio telescopes, hoping to detect patterns in the cosmic static that would indicate intelligent origin. But radio signals represent just one possible technological signature among countless ways that advanced civilizations might make their presence known across interstellar distances. Understanding what intelligent alien technology might reveal means thinking beyond communication attempts to consider the inevitable side effects and engineering projects that any sufficiently advanced civilization would produce. Technology leaves traces. Human civilization has only been producing radio signals for about a century. Yet already, our technological fingerprint extends outward in a sphere over 200 light-years in diameter, expanding at the speed of light. Television broadcasts, radar installations, radio communications, all of this electromagnetic radiation leaks into space, creating a bubble of human-generated signals spreading through the galaxy. An alien civilization with sensitive enough radio telescopes could detect these signals and know that an industrial, technological species exists on Earth, even if we never intentionally try to contact them. Our technology reveals us whether we choose to advertise our presence or not. The same principle applies to alien civilizations. Any technological species using electromagnetic radiation for communication, navigation, or industrial processes would inadvertently create detectable signals. The frequency, pattern, and characteristics of these signals would differ from natural astronomical sources. Natural radio emissions from stars, nebulae, and other cosmic objects tend to be broadband, spread across a wide range of frequencies, or if narrowband, they're produced by specific atomic or molecular transitions at predictable frequencies. Artificial signals, in contrast, might be extremely narrowband, might drift in frequency in patterns that reflect the relative motion of transmitter and receiver, or might contain modulations and patterns that have no natural explanation. The famous WOW signal detected in 1977 by the Big Ear radio telescope at Ohio State University demonstrated what a potential technosignature might look like. For 72 seconds, the telescope received a strong, narrow-band signal from the direction of the constellation Sagittarius. The signal was so unusual that astronomer Jerry Amon wrote "WOW" on the printout, giving the detection its name. The signal has never been detected again, despite decades of subsequent observations, and its origin remains unexplained. It might have been terrestrial interference, or a reflection off space debris, or a natural phenomenon we don't yet understand, or it might have been exactly what it appeared to be, a brief, powerful transmission from an alien source that was never repeated. Optical signals represent another detection method. Laser technology on Earth has advanced to the point where powerful lasers could, in principle, outshine the sun at specific wavelengths for brief moments. If we pointed a sufficiently powerful laser at a star, an alien astronomer observing from that star system might detect the flash, recognizing it as artificial because of its extreme brightness at a single wavelength. This is the basis for optical SETI, the search for brief, intense laser pulses from other civilizations. Aliens might use lasers for interstellar communication because lasers are highly directional and can carry large amounts of information. A civilization intentionally trying to contact other species might beam powerful laser pulses toward nearby stars, hoping someone is watching. But some of the most compelling technosignatures might come not from communication attempts, but from large-scale engineering projects. Any advanced civilization would need energy, and energy requirements grow as civilizations become more technologically sophisticated. In 1964, physicist Freeman Dyson proposed that a sufficiently advanced civilization might construct a vast structure around its star to capture a significant fraction of the star's total energy output. This structure, called a Dyson sphere or Dyson swarm, might consist of countless solar panels, habitats, or other components orbiting the star, intercepting sunlight and converting it to useful energy. A complete Dyson sphere would make the star invisible at visible wavelengths. All the light would be absorbed by the structure, but the structure would glow in infrared radiation, emitting the waste heat from whatever processes the captured energy powered. From a distance, a star surrounded by a Dyson sphere would appear anomalously bright in infrared, while being dim or invisible in visible light. Astronomers have searched for such infrared excess stars, cataloguing objects that might be Dyson spheres. Though all candidates discovered so far have more mundane explanations like dust clouds or unusual stellar properties. Megastructures don't need to enclose entire stars to be detectable. A single, enormous structure in orbit around a star might block a tiny fraction of the star's light as it passes in front of the star from our perspective. This would create a transit, a dip in the star's brightness, similar to what happens when a planet transits its star. But while planetary transits follow regular, predictable patterns with consistent depths and durations, a megastructure might create irregular, asymmetric transits that don't match any natural explanation. The star KIC 84462852, also known as Tabby's star after astronomer Tabitha Boyajian, who led the research team that discovered its unusual behaviour, demonstrated what such anomalies might look like. This star, observed by the Kepler Space Telescope, exhibited irregular, dramatic dips in brightness, sometimes dropping by more than 20%, that didn't match the patterns expected from planets, dust clouds, or any other standard astronomical explanation. The irregular timing and unusual shapes of the dimming events led some researchers to speculate about megastructures, though most scientists now favour natural explanations involving dust and debris, possibly from a disintegrating comet or planet. Still, Tabby's star showed that we could detect anomalous dimming patterns, and if megastructures exist, similar observations might reveal them. Atmospheric pollution represents a more subtle, but potentially detectable, technosignature. Industrial civilizations inevitably alter their planet's atmosphere through their activities. On Earth, the Industrial Revolution increased carbon dioxide levels, added artificial chemicals like chlorofluorocarbons, and changed atmospheric chemistry in detectable ways. Some proposed technosignatures involve looking for molecules in exoplanet atmospheres that shouldn't exist naturally. Chlorofluorocarbons, for instance, are entirely artificial. They don't form through natural processes, but are produced industrially. Detecting CFCs in an exoplanet's atmosphere would be strong evidence for industrial activity. Similarly, nitrogen dioxide concentrations above natural levels could indicate industrial combustion. Certain combinations of atmospheric gases might indicate technological activity. For example, large amounts of both oxygen and methane in the same atmosphere shouldn't coexist naturally because these gases react with each other. If both are abundant, something must be continuously producing them. While biology can produce both gases, certain ratios or the presence of specific isotopes might point toward industrial rather than biological sources. City lights offer another potential technosignature. Earth's night side is dramatically brighter than it was before artificial lighting, with cities visible from space as brilliant concentrations of light. An alien civilization observing Earth with sufficiently powerful telescopes could detect this artificial illumination, recognizing it as technological in origin because the light spectrum differs from natural phenomena like forest fires or volcanic activity. The light would also be concentrated in specific patterns, along coastlines, in networks of roads, around population centers, rather than being randomly distributed. Detecting city lights on exoplanets would be extraordinarily challenging with current technology. The light from the planet's star overwhelms the faint glow of artificial lighting by enormous margins. But future telescopes, particularly those designed to directly image exoplanets by blocking the star's light, might have the sensitivity to detect bright illumination on a planet's night side, especially if the civilization uses inefficient lighting that wastes energy as light escaping into space, rather than being directed downward toward the ground. Space-based infrastructure might be detectable through reflected light or occultations. Satellites, space stations, solar panel arrays, and other orbital structures reflect light from their star. A civilization with extensive orbital infrastructure might create a faint cloud of reflected light around their planet, detectable as excess brightness beyond what the planet itself would reflect. Similarly, large orbital structures might occasionally pass in front of stars in the background as seen from Earth, creating very brief, tiny dips in brightness that could be detected through careful monitoring. Propulsion systems represent another potential technosignature. Any civilization attempting interstellar travel would need enormous energy to accelerate spacecraft to significant fractions of light speed. Some proposed propulsion systems would create detectable signatures. Nuclear pulse propulsion, using nuclear explosions for thrust, as proposed in the Orion project, would create distinctive radiation signatures. Antimatter engines would produce gamma rays from matter-antimatter annihilation. Fusion drives would create specific spectral signatures from the fusion reactions. Even laser-pushed light sails, sails accelerated by powerful lasers from the home star system, would create bright laser beams visible across interstellar distances to anyone positioned along the beam's path. Gravitational engineering, if possible, might create detectable anomalies. If advanced civilizations can manipulate gravity or space-time, something beyond our current technological capabilities, but not necessarily forbidden by physics, their activities might create detectable effects. Artificial gravitational waves at unusual frequencies, anomalous motions of stars or planets that suggest artificial manipulation, or regions of space with unexplained gravitational properties could all potentially indicate advanced technology at work. Asteroid mining and large-scale resource extraction would alter the appearance of solar systems. A civilization mining asteroids for raw materials would change the distribution and size of asteroids over time. Spectroscopic observations might reveal unusual compositions in asteroid belts, perhaps unusually low concentrations of useful metals if those metals have been extensively mined. Debris from mining operations might create distinctive dust clouds with unusual properties. Stellar engineering represents the extreme end of technological signatures. Some theorists have proposed that advanced civilizations might manipulate stars themselves, extracting material from stars, changing stellar composition, or even moving stars through space using enormous thrusters. These Shkadov thrusters, named after physicist Leonid Shkadov, would use mirrors or other structures to create thrust from a star's own radiation pressure, allowing the star to be slowly moved over millions of years. A civilization might move their star to escape dangers like nearby supernovae, to position their star system optimally in the galaxy, or to transport their entire solar system on an interstellar journey. A moving star whose motion couldn't be explained by gravitational interactions with other objects might indicate such stellar engineering. Time also factors into detectability. A civilization's technological signatures change as technology evolves. Humanity's radio era might be brief, perhaps only a few centuries between when we developed radio technology and when we transitioned to communication methods that don't leak into space, like fiber optics or directed transmissions. An alien civilization might have a similarly brief radio-loud period. This means that civilizations at different technological stages would produce different signatures. An early industrial civilization might produce atmospheric pollution, but no radio signals. A spacefaring civilization might have extensive orbital infrastructure, but might no longer use radio for communication. An extremely advanced civilization might produce signatures we cannot yet imagine, using technologies and engineering approaches completely beyond our current conceptual framework. The absence of detected technosignatures, despite decades of searching, has led to discussions of the Fermi paradox. If technological civilizations are common, where are their signatures? Perhaps they're too rare or too distant. Perhaps they exist but avoid broadcasting or producing detectable signatures intentionally. Perhaps our detection methods are inadequate or focused on the wrong signatures. Or perhaps advanced civilizations develop technologies that produce no detectable signatures, or signatures we wouldn't recognize because we're not looking for them. What intelligent alien technology might reveal encompasses everything from deliberate messages transmitted across space to the inevitable waste heat and pollution from industrial processes, from the dimming of stars caused by megastructures to the reflected light from orbital infrastructure, from laser flashes used for communication to the gravitational anomalies created by stellar engineering. Each technological signature represents a different window into how civilizations develop, what they value, what problems they solve, and how they reshape their environments. Detecting any of these signatures would answer one of humanity's deepest questions: are we alone? And would provide our first glimpse into how other intelligences have developed technology, overcome challenges, and left their mark on the cosmos, transforming our understanding of what's possible, and revealing that the universe contains not just stars, planets, and lifeless matter, but minds that contemplate the cosmos just as we do, minds that build and create and reach toward the stars. Why alien life might not use DNA, deoxyribonucleic acid, is the molecule of heredity for nearly all life on Earth. From bacteria to blue whales, from mushrooms to sequoia trees, every organism uses DNA to store genetic information, to pass traits from parents to offspring, and to direct the construction of proteins that build and maintain living cells. DNA's structure is elegant and famous, a double helix of two strands twisting around each other, each strand composed of a sugar phosphate backbone with 4 types of bases attached in sequences that encode genetic instructions. DNA seems so fundamental to life that it's easy to assume it must be universal, that any living thing anywhere in the universe would use DNA. But this assumption is almost certainly wrong. DNA is not the only molecule capable of storing and transmitting genetic information, and the specific chemistry that makes DNA work on Earth might not be optimal or even possible under different planetary conditions. To understand why alien life might not use DNA, we first need to understand what DNA actually does and what properties make it suitable for its role. DNA serves 3 critical functions. First, it stores information. The sequence of bases along the DNA strand encodes instructions for building proteins and regulating cellular processes. Second, it replicates. DNA can be copied with reasonable accuracy, allowing genetic information to be passed from one generation to the next. Third, it allows variation. Copying isn't perfect, and occasional errors introduce mutations that create the genetic diversity necessary for evolution. But DNA is not unique in performing these functions. Scientists have created synthetic alternatives called XNAs, xenonucleic acids, that can store information, be copied, and undergo evolution despite having different chemical structures than DNA. These molecules use different sugars in their backbones, 3-O's instead of deoxyribose, locked nucleic acids with modified sugars, or even molecules with completely different backbone structures. These XNAs can form base pairs, store sequences of information, and be replicated by specialized enzymes. They demonstrate conclusively that DNA is not the only possible genetic molecule, merely the one that happened to work on Earth. The chemistry of DNA is optimized for Earth's conditions. DNA is stable in liquid water at temperatures roughly between 0 and 40 degrees Celsius, the temperature range where most Earth life operates. The hydrogen bonds holding the two strands together are strong enough to keep the double helix intact, but weak enough that the strands can be separated for copying. The sugar phosphate backbone is stable in water at neutral pH, but can be broken down by enzymes when necessary. The bases, adenine, thymine, guanine, and cytosine, are moderately stable molecules that can withstand normal cellular conditions, but can be damaged by extreme heat, intense radiation, or strongly acidic or alkaline environments. On a planet with very different conditions, DNA might not function well or at all. Consider a world much hotter than Earth, perhaps a planet orbiting very close to its star, with surface temperatures exceeding 100 degrees Celsius, but with liquid water kept stable by extreme atmospheric pressure. At these elevated temperatures, DNA becomes increasingly unstable. The hydrogen bonds holding the two strands together weaken and break more easily. The chemical bonds in the bases and the backbone break down more rapidly. Organisms on such a world would need genetic molecules more heat-resistant than DNA, perhaps with stronger chemical bonds, more stable base structures, or completely different architectures that maintain integrity at high temperatures. Some Earth organisms that thrive in extreme heat have evolved DNA repair mechanisms that constantly fix damage to their genetic material, but there are limits to how hot DNA can tolerate. Beyond a certain temperature, the rate of damage exceeds the capacity of repair mechanisms to fix it. Alien life on a hot world might evolve an alternative genetic molecule with inherently greater thermal stability, perhaps using bases with stronger bonding, or sugars that resist thermal degradation, or entirely different building blocks that remain stable at temperatures where DNA would fall apart within seconds. At the opposite extreme, very cold worlds present different challenges. DNA becomes more rigid at low temperatures, making it harder to separate the strands for copying. The enzymes that copy DNA become less efficient or stop working entirely when too cold. Life on an extremely cold world, perhaps on a moon like Titan, where temperatures hover around -180 degrees Celsius, would need genetic molecules that remain flexible and functional at these frigid temperatures. The chemistry would necessarily be different from DNA, which was shaped by evolution to function in Earth's moderate temperature range. The solvent environment profoundly affects what genetic molecules are possible. DNA functions in liquid water, and its chemical properties are specifically suited to aqueous environments. The sugar phosphate backbone is hydrophilic, attracted to water, which helps keep DNA dissolved in cellular fluids. The bases are hydrophobic, repelled by water, which helps drive base pairing by pushing bases toward each other and away from the surrounding water. This balance creates DNA's structure and stability. In a different solvent, liquid methane, liquid ammonia, or something even more exotic, DNA's chemistry wouldn't work the same way. Water's polarity, its hydrogen bonding capacity, its ability to dissolve certain substances while excluding others. All these properties shape how DNA behaves. In liquid methane, a non-polar solvent, molecules that are hydrophobic in water might become soluble, while hydrophilic molecules might be insoluble. A genetic molecule designed for a methane-based solvent would need completely different chemical properties than DNA, perhaps with non-polar groups exposed to interact with the methane solvent, and polar groups hidden in the molecule's interior. The availability of raw materials constrains what genetic molecules can be built. DNA requires phosphorus, nitrogen, carbon, oxygen, and hydrogen. Phosphorus, though essential for DNA's backbone, is relatively rare in the universe compared to lighter elements. A planet poor in phosphorus might not be able to build DNA-like molecules and would need to evolve genetic systems based on more abundant elements. Perhaps silicon could replace phosphorus in the backbone, or sulfur could play a role, or arsenate, a chemical similar to phosphate, might substitute. Though experiments with arsenate-based DNA on Earth showed it's much less stable than normal DNA. The 4-base system used by DNA, adenine, thymine, guanine and cytosine, is not the only possible coding scheme. RNA, DNA's chemical cousin, uses uracil instead of thymine, demonstrating that the specific bases aren't fixed. In principle, genetic molecules could use 3 bases, or 6 or even more. More bases would allow more information to be encoded in shorter sequences. With 4 bases, each position in the sequence can encode 2 bits of information, but with 8 bases, each position could encode 3 bits. An alien genetic system might use more or fewer bases depending on what works best with its chemistry. Some scientists have even created expanded genetic alphabets, DNA-like molecules with additional base pairs beyond the natural 4. These synthetic genetic systems can store more information per unit length than natural DNA and can be copied by modified enzymes. The existence of these expanded alphabets demonstrates that the 4-base system is not uniquely optimal, but rather reflects the specific chemistry that evolved on Earth. Alien life might independently evolve genetic systems with different numbers of bases encoding information in different ways. The structure of the genetic molecule might differ radically from DNA's double helix. DNA forms a helix because of how the bases pair and how the sugar phosphate backbone bends, but other structures are possible. Some XNAs form helices with different geometries, left-handed instead of right-handed, wider or narrower than DNA, with more or fewer base pairs per helical turn. Some synthetic genetic molecules don't form helices at all, but adopt completely different 3-dimensional structures. An alien genetic molecule might be a triple helix, a quadruple helix, a ladder without a twist, or some topology we haven't imagined. The copying mechanism might also differ. DNA is copied by enzymes called polymerases that move along the DNA strand, reading the sequence and creating a complementary new strand. This process requires a complex molecular machinery that evolution has refined over billions of years on Earth. Alien life might evolve completely different copying mechanisms, perhaps catalytic RNA-like molecules that copy themselves without protein enzymes, or inorganic crystals that template the formation of complementary structures, or even copying processes that don't involve template-directed synthesis at all, but rather some form of self-assembly guided by the genetic molecule structure. The rate of mutation, how often copying errors occur, affects evolution's pace. DNA polymerases on Earth make errors at a rate of roughly 1 mistake per billion bases, copied for the most accurate enzymes, though rates vary. This error rate is low enough to preserve genetic information across generations, but high enough to generate the variation necessary for evolution. Alien genetic systems might have very different error rates. A system with much lower error rates would evolve more slowly, potentially making adaptation difficult. A system with higher error rates might generate variation faster, but risk genetic information degradation. The optimal error rate depends on generation time, selection pressure, and environmental stability. RNA represents an alternative genetic molecule that exists on Earth and might have preceded DNA in evolution. RNA can store information, catalyze chemical reactions, and replicate all functions DNA cannot perform alone. The RNA world hypothesis proposes that early life used RNA as both genetic material and catalytic molecule before DNA and proteins evolved. An alien world might develop life that remains in an RNA world-like state, never evolving DNA, or might evolve RNA into forms more sophisticated than anything on Earth, creating genetic systems based on elaborate RNA structures rather than DNA. Some scientists have speculated about non-molecular genetic systems. Perhaps information could be stored in the crystal structure of inorganic minerals, with patterns of inclusions, defects, or layering encoding information that could be replicated when crystals grow and form templates for new crystals. Or perhaps information could be stored in magnetic domains in iron-rich minerals, with the orientation of magnetic fields encoding genetic instructions. These ideas are highly speculative and face enormous challenges. How would such systems be read and translated into functional structures? But they illustrate that genetic information storage might not require organic molecules at all. The universality of certain aspects of information storage might transcend specific chemistry. Any genetic system, whether based on DNA, XNA, RNA, or something entirely different, must be able to store discrete, sequential information, symbols arranged in order that can be read and interpreted. This is fundamentally a problem of information theory rather than chemistry. The specific physical substrate that stores the information might be less important than the information itself, and the mechanisms for reading, copying, and translating it into functional structures. If we ever detect alien life, determining its genetic system would be among the first questions we'd want to answer. If alien life uses DNA with the same 4 bases and same genetic code as Earth life, it would suggest either that DNA is universally optimal, unlikely given all the possible alternatives, or that Earth life and alien life share a common origin, perhaps through panspermia. The hypothesis that life can spread between worlds via meteorites or comets. Finding alien life with completely different genetic molecules would confirm that life can independently originate using different chemistry, revealing that DNA is merely one solution among many to the problem of heredity. The genetic code, the mapping between base sequences and amino acids, might also differ. Earth's genetic code is nearly universal across all life, with 3 base sequences called codons specifying which amino acid to insert when building proteins. But the specific assignment of codons to amino acids appears somewhat arbitrary. There's nothing inherent in the chemistry of the codon UUU that demands it code for the amino acid phenylalanine rather than some other amino acid. The code seems to be a frozen accident. Once it was established early in evolution, changing it would be catastrophic because it would alter the meaning of every gene, so it became locked in place. Alien life would likely evolve a completely different genetic code, with different codon assignments, and possibly even a different codon length. 2 base codons, or 4 base codons, or variable length codons. Why alien life might not use DNA comes down to DNA being a solution specific to Earth's conditions. Liquid water at moderate temperatures, specific pH ranges, availability of particular elements, and the accidents of chemical evolution that occurred during life's origin on our world. Different conditions would favour different molecules, and even similar conditions might allow evolution to discover different solutions. DNA is remarkable and elegant, but it's not magic or inevitable. It's chemistry, sophisticated, evolved chemistry that works beautifully on Earth, but that represents just one possible answer to the fundamental question of how to store, copy, and transmit genetic information across generations. Across the universe, life might employ countless different genetic systems, each one adapted to its world's unique conditions, each one encoding information and enabling heredity through different molecular mechanisms, proving that while the principle of heredity might be universal wherever life exists, the specific molecular machinery implementing that heredity can vary as widely as the diversity of worlds themselves. with DNA being merely Earth's particular solution to the universal challenge of passing genetic information from parent to offspring through the generations. Why alien life might be microscopic. When we imagine alien life, our minds often conjure images of intelligent beings piloting spacecraft, complex organisms with eyes and limbs exploring alien landscapes, or at minimum, creatures we could observe and recognize as alive. But this expectation might be profoundly misguided. Earth's history offers a sobering perspective. For roughly 3 billion of the 4 billion years that life has existed on our planet, all organisms were microscopic. Bacteria, archaea, and single-celled eukaryotes dominated Earth's biosphere for the vast majority of life's history. Complex multicellular organisms, plants, animals, fungi, are recent arrivals, having existed for less than 1 billion years. If Earth's timeline is any indication, most life in the universe might be microscopic, existing as single cells or simple colonies that never evolve into the complex macroscopic forms we're accustomed to seeing. The transition from single-celled to multicellular life represents one of the most difficult evolutionary innovations in Earth's history. It only happened once in the bacterial lineage, never successfully transitioning beyond simple filaments and colonies, and only a few times in the eukaryotic lineage, producing plants, animals, and fungi. This rarity suggests that while single-celled life might emerge relatively easily wherever conditions permit, the evolution of complex multicellularity requires specific circumstances that might not commonly occur. Many alien worlds might develop thriving microbial biospheres that remain forever microscopic because the evolutionary innovations needed for large, complex organisms never occur. Energy availability represents the first major constraint on complexity. Complex multicellular organisms require substantial energy to build and maintain their bodies. They need energy to power specialized organs, to move through their environments, to grow to large sizes. Most of this energy ultimately comes from oxygen-based metabolism, which releases far more energy per molecule of food than anaerobic metabolism does. The efficiency of oxygen metabolism, about 15 times more energetic than the best anaerobic alternatives, enabled the evolution of large active organisms on Earth. But oxygen was not always available in Earth's atmosphere. For the first 2 billion years or more of life's existence, the atmosphere contained very little free oxygen. Life during this time remained entirely microscopic and relatively simple, constrained by the low energy yields of anaerobic metabolism. Only after photosynthetic bacteria evolved and began producing oxygen as a waste product did atmospheric oxygen accumulate, and only after oxygen reached substantial levels could organisms evolve the high-energy metabolisms necessary for large size and complexity. Many alien worlds might never undergo this transition. If photosynthetic life never evolves, or if it evolves but produces different waste products, perhaps using electron donors other than water that don't release oxygen, the atmosphere might remain oxygen poor indefinitely. Life on such worlds would be permanently restricted to anaerobic metabolism, with its inherent energy limitations preventing the evolution of large complex organisms. The biosphere might flourish with countless microscopic species filling every available niche, but nothing larger than perhaps a millimeter would ever evolve, because the energy budgets of anaerobic metabolism cannot support larger sizes or more complex structures. Predation drives much of the evolution toward complexity on Earth. The development of predators created selection pressure for prey to evolve defenses, armor, toxins, multicellularity that makes them too large to be consumed by single-celled predators. Predators, in turn, evolved mechanisms to overcome these defenses: better sensing systems, faster movement, cooperative hunting. This evolutionary arms race between predators and prey drove increasing complexity with both sides becoming more sophisticated over generations. The transition to multicellularity in animals might have been driven at least partially by predation pressure from other single-celled organisms. On an alien world where predation never becomes significant, perhaps because environmental conditions don't favor the evolution of heterotrophs, or because chemical energy is so abundant that organisms don't need to consume each other, this driver of complexity would be absent. Life might remain a collection of bacteria-like organisms metabolizing chemicals from their environment, with no selection pressure favoring the evolution of larger, more complex forms. Without predation or competition driving an evolutionary arms race, the biosphere might reach an equilibrium of simple, efficient microorganisms that persist unchanged for billions of years. The evolution of eukaryotic cells, cells with nuclei and complex internal structures, required an extraordinarily unlikely event called endosymbiosis, where one cell engulfed another and instead of digesting it, established a permanent symbiotic relationship. On Earth, mitochondria, the energy-producing organelles in eukaryotic cells, originated as free-living bacteria that were engulfed by other cells and eventually became integrated parts of those cells. This event, which happened roughly 2 billion years ago, was apparently unique in Earth's history. It happened once, and all eukaryotic cells descend from that single event. Eukaryotic cells made complex multicellular life possible. Their mitochondria provide far more energy per cell than bacteria can generate, allowing cells to support larger genomes and more complex structures. Their internal compartmentalization allows specialized biochemistry to occur in different cellular regions. Their complex cytoskeletons enable intricate cell shapes and coordinated movements. Without eukaryotic cells, complex multicellular organisms probably could not evolve. If endosymbiosis was difficult, requiring very specific circumstances to occur even once on Earth, alien worlds might never undergo this transition. Life might remain forever bacterial, lacking the cellular complexity necessary as a foundation for multicellular organisms. These worlds would have rich microbial ecosystems with tremendous diversity at the microscopic level, but would never produce organisms visible to the naked eye. Environmental stability influences evolutionary innovation. Earth's environment has been highly variable over geological time. Ice ages, warming periods, asteroid impacts, volcanic catastrophes, changing atmospheric composition, continents drifting and colliding. These environmental changes created selection pressures that favored adaptability and innovation. Mass extinctions wiped out dominant groups, allowing new forms to radiate and diversify. Without such disruptions, dominant organisms might remain unchanged indefinitely, never facing circumstances that favor more complex alternatives. An alien world with a remarkably stable climate and environment over billions of years might never see complex life evolve. Early microbial ecosystems might reach an equilibrium where existing organisms are so well adapted to unchanging conditions that no complex innovations provided advantages. Microbes would efficiently fill every niche, processing every available chemical, extracting every erg of available energy, and no evolutionary pressure would favor the metabolically expensive transition to larger, more complex forms. The planet would remain microbial forever, not because complex life is impossible, but because stable conditions never create circumstances where complexity is advantageous. The availability of ecological niches affects diversification. On Earth, new environmental niches continuously opened as continents drifted, climates changed, and oxygen accumulated in the atmosphere. Moving onto land created entirely new sets of niches, terrestrial environments with different challenges than aquatic ones. Flying created another set of niches. Each new opportunity drove adaptive radiations, where organisms evolved to exploit newly available resources and habitats. A planet lacking this niche diversity might not provide opportunities for complex life to evolve. A world completely covered by ocean with no land would lack terrestrial niches. A world with a homogeneous environment, perhaps a global ocean with uniform temperature and chemistry from pole to pole, would offer fewer distinct niches than Earth's highly varied environments. With fewer niches available, there would be less opportunity for adaptive radiation and less selection pressure driving organisms toward the specializations and complexities that fill diverse ecological roles. Timescales matter significantly. Evolution proceeds through random mutations and natural selection, accumulating beneficial changes over countless generations. Complex innovations require many individual evolutionary steps, each one building on previous changes. The evolution of eyes, for instance, required the initial evolution of light-sensitive proteins, then the gathering of these proteins into light-sensitive patches, then the invagination of these patches into cups that provide directional information, then the development of lenses that focus light, then the neural processing systems to interpret visual information. Each step took many generations and many mutations. On an alien world where organisms have very long generation times, perhaps living for thousands of years before reproducing, evolution would proceed extraordinarily slowly. A complex innovation that might evolve in tens of millions of years on Earth, where many organisms reproduce annually or even faster, might take billions of years on a world where generation times are measured in millennia. If the planet star has a relatively short lifetime, perhaps a massive star that will exhaust its fuel in a few billion years, there might simply not be enough time for complex life to evolve before the star's death sterilizes the planet. The chemical environment limits biological complexity. Complex organisms require diverse biochemistry, proteins for structure and catalysis, lipids for membranes, nucleic acids for information storage, carbohydrates for energy and structure. Building these diverse molecules requires access to various elements in appropriate forms. A planet poor in essential elements, perhaps lacking sufficient phosphorus, nitrogen, sulfur, or trace metals, might not provide the chemical building blocks necessary for complex biochemistry. Life might arise using simpler chemistry, but might be unable to evolve the molecular diversity needed for complex cells and multicellular structures. Physical constraints on size affect what complexity is possible. Surface tension becomes increasingly important at small scales. For microscopic organisms living in water, surface tension is a significant force. Water behaves more like thick syrup than like the thin fluid humans experience. Moving through water at microscopic scales requires different strategies than swimming at macroscopic scales. These physical differences mean that microorganisms experience a fundamentally different physical world than large organisms, and the adaptations that work well at microscopic scales might not scale up successfully. The speed of light sets absolute limits on how quickly information can be transmitted within an organism. For microscopic cells, this is never a constraint. Signals cross the cell in negligible time. But as organisms grow larger, signal transmission times become significant. A 1-meter organism experiences light travel times of about 3 nanoseconds, still essentially instantaneous for chemical and neural signals. But organisms must coordinate their parts, and this coordination becomes more difficult as size increases. Neural signals in humans travel at speeds of about 100 meters per second, meaning signals take milliseconds to travel from extremities to brain. For a hypothetical organism many meters or kilometers in size, coordination would become increasingly difficult. Detection bias affects our perception of what life looks like. Humans evolved to perceive objects roughly our own size. We see animals, plants, and landscape features easily because our sensory systems are optimized for that scale. Microscopic organisms are invisible without technological assistance. An alien observer visiting Earth equipped with sensing systems similar to human vision might conclude that Earth has relatively little life, missing entirely the vast microbial world that actually dominates in terms of biomass, diversity, and metabolic activity. Similarly, when we search for alien life, our methods tend to focus on detecting macroscopic effects, oxygen in atmospheres produced by photosynthetic organisms, changes in planetary albedo from vegetation, perhaps even artificial lights from technological civilizations. A planet covered in microbial life, producing no oxygen, with no multicellular organisms, with nothing visible at planetary scales, might appear lifeless to our telescopes, even if it hosts an incredibly rich and diverse microbial biosphere. Statistical considerations based on Earth's history suggest that if we discovered alien life, it would most likely be microscopic. Life existed on Earth for about 3 billion years before complex multicellular organisms evolved. If we randomly selected a moment in Earth's history, there would be a roughly 75% chance of finding only microscopic life. Assuming Earth's timeline is typical, which may or may not be true, most inhabited planets at any given time would be in their microbial phase, with complex life being relatively rare. Why alien life might be microscopic comes down to microbial life being easy to achieve relative to complex life, requiring only basic metabolism, reproduction, and evolution, while complex life requires numerous specific evolutionary innovations, oxygenic photosynthesis or equivalent high-energy metabolism, eukaryotic cells with their mitochondrial endosymbionts, multicellularity with coordinated cells working together, specialized tissues and organs, each one potentially rare or slow to evolve. Many worlds might develop thriving microbial ecosystems within their first billion years, but might never progress beyond that stage, remaining forever inhabited by bacteria-like organisms invisible to the naked eye, yet representing the most common form of life in the universe. A cosmos filled not with civilizations or even visible organisms, but with countless worlds hosting microbial biospheres that flourish in every conceivable environment, from sunlit surface waters to deep subsurface rocks, from hydrothermal vents to subsurface oceans beneath ice. Each microscopic cell representing a success story of evolution in its own right, reminding us that complexity and large size are not prerequisites for biological success, and that if we ever detect life beyond Earth, we should not be disappointed if it consists of nothing more than microbes, because microbial life might be life's most common, most successful, most enduring form across the vast expanse of the living universe. What is dark matter, and why can't we see it? Imagine trying to understand a conversation in a crowded room while wearing earplugs. You can see people's mouths moving, see their gestures, watch them react to each other, but you can't hear the words being spoken. You know communication is happening, the evidence is clear in the movements and responses, but the medium of that communication remains completely inaccessible to you. This is somewhat like humanity's relationship with dark matter. We can see its effects throughout the universe, observe how it shapes galaxies and bends light, measure its gravitational influence on everything around it, yet the substance itself remains invisible and intangible to every instrument we've built to observe the cosmos. Dark matter makes up approximately 85% of all matter in the universe. Let that sink in for a moment. Everything you can see, every star, every galaxy, every glowing nebula, every planet, every atom in your body represents only about 15% of the matter that exists. The rest, the overwhelming majority, is dark matter, and it surrounds us, permeates us, flows through us, yet reveals itself only through its gravitational effects. The story of dark matter's discovery begins not with a sudden revelation, but with decades of observations that didn't quite make sense. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a collection of over 1,000 galaxies bound together by gravity. He measured how fast these galaxies were moving within the cluster and used these velocities to calculate how much mass must be present to keep the cluster gravitationally bound. What he found was shocking. The galaxies were moving so fast that they should have escaped the cluster's gravity and flown apart long ago, unless the cluster contained far more mass than could be seen in the form of stars and gas. Zwicky proposed that some form of dark matter must exist, matter that didn't emit light but provided the additional gravity needed to hold the cluster together. His idea was largely ignored for decades. It seemed too radical, too strange. Surely there was a simpler explanation. Perhaps astronomers were just missing some normal matter, dust clouds or dim stars that hadn't been detected yet. But the evidence kept accumulating. In the 1970s, astronomer Vera Rubin conducted detailed studies of how stars and gas move within spiral galaxies. According to the laws of gravity and orbital mechanics, objects farther from the center of a galaxy should move more slowly, just as planets farther from the Sun orbit more slowly than those closer in. Mercury races around the Sun in just 88 days, while distant Neptune takes 165 years to complete one orbit. The same principle should apply to galaxies. Stars near the edge should crawl along in their orbits compared to stars closer to the galactic center. But that's not what Rubin found. She observed that stars at the outer edges of galaxies moved just as fast as stars closer to the center, sometimes even faster. The rotation curves of galaxies were flat rather than declining, which could only mean one thing. There was far more mass in these galaxies than could be accounted for by visible stars and gas. And this extra mass wasn't concentrated at the center where most of the visible matter was. It extended far beyond the visible disk, forming a massive spherical halo of invisible matter surrounding each galaxy. Picture a galaxy in your mind, a spiral with graceful arms of stars spinning around a bright central bulge. Now imagine that entire visible structure is embedded within a much larger sphere of dark matter, extending perhaps 10 times farther than the visible stars reach. This dark matter halo contains several times more mass than all the stars, gas and dust combined, yet it emits no light, no radio waves, no X-rays, nothing we can detect directly. The evidence for dark matter extends far beyond galaxy rotation curves. Gravitational lensing provides some of the most compelling proof. According to Einstein's theory of general relativity, mass warps the fabric of spacetime, and light follows the curves in this warped spacetime. When light from a distant galaxy passes near a massive object, its path bends. Just as light bends when passing through a glass lens. The amount of bending depends on how much mass is present. Astronomers observe light from distant galaxies being bent and distorted as it passes through galaxy clusters. By measuring this distortion carefully, they can map out exactly where mass is concentrated in these clusters, creating what's essentially a gravity map. When they do this, they find that most of the mass, about 90%, isn't where the visible galaxies are. It's distributed in a much larger structure, consistent with massive halos of dark matter. One of the most dramatic examples came from studying a structure called the Bullet Cluster, where two galaxy clusters had collided and passed through each other. During the collision, the hot gas from each cluster, which is normal matter, slowed down and remained near the collision site, heated by the impact. But the dark matter from each cluster, which doesn't interact with normal matter except through gravity, passed right through and continued moving. By mapping the gravity through gravitational lensing, astronomers could see that most of the mass had separated from the visible gas providing direct evidence that dark matter and normal matter are distinct substances. So what is dark matter made of? This is one of the deepest mysteries in physics. And the honest answer is that we don't know. We know what it isn't. It's not made of atoms, protons, neutrons, or electrons. It's not any form of normal matter that we're familiar with. We call normal matter baryonic matter, and dark matter is something entirely different, something that exists outside the catalogue of particles that make up everything we can touch and see. The most popular hypothesis is that dark matter consists of particles that simply don't interact with electromagnetic radiation. Light, radio waves, X-rays, any form of light across the entire spectrum. These hypothetical particles, often called WIMPs, weakly interacting massive particles, would have mass and exert gravity, but they wouldn't emit, absorb, or reflect light. They would be essentially transparent to electromagnetic radiation, which is why we can't see them. Imagine a particle that could pass through matter almost as if it weren't there. Billions of these particles might be flowing through your body right now, passing through the Earth, streaming through space, and you would never know. They don't collide with atoms, don't scatter off electrons, don't leave any trace except for their collective gravitational influence. This is what dark matter particles would be like. Ghost particles that fill the universe, but interact with normal matter only through the weakest of forces. Scientists have built incredibly sensitive detectors deep underground, shielded from cosmic rays and background radiation, trying to catch the rare interaction of a dark matter particle with normal matter. These detectors contain tanks of specially purified materials, cooled to near absolute zero, instrumented with sensors that can detect the tiniest energy deposit. The idea is that occasionally, very rarely, a dark matter particle might collide with a nucleus in the detector, releasing a tiny amount of energy that could be measured. So far, despite decades of searching with increasingly sensitive experiments, no one has definitively detected a dark matter particle. Another possibility is that dark matter consists of primordial black holes that formed in the early universe, not from collapsing stars, but from density fluctuations shortly after the Big Bang. These would be dark by their very nature, since black holes don't emit light. However, careful observations suggest that primordial black holes can't account for all the dark matter. They would produce observable effects, like gravitational microlensing when they pass in front of distant stars. And we don't see these effects at the level that would be expected if most dark matter were in this form. Some theories propose that dark matter might be axions, extremely light particles that were produced in enormous quantities in the early universe. These would be very different from WIMPs, much lighter, much more numerous, behaving more like a wave than individual particles. Detecting axions requires different experimental approaches, and several experiments are currently searching for these elusive particles. There's even a possibility, though most physicists consider it less likely, that dark matter doesn't exist at all. Instead, perhaps our understanding of gravity is incomplete, and the theory needs to be modified to explain the observations without requiring invisible matter. These modified gravity theories, called MOND, modified Newtonian dynamics, and various relativistic extensions, can explain some observations but struggle with others, like the bullet cluster, which seems to require actual dark matter to explain. Dark matter played a crucial role in the formation of structure in the universe. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly, with only tiny variations in density. These variations were the seeds of all future structure: galaxies, galaxy clusters, and the cosmic web. But normal matter coupled to radiation in the early universe couldn't collapse and clump together efficiently. Dark matter, which didn't interact with radiation, could begin collapsing earlier, forming gravitational wells that normal matter eventually fell into. Without dark matter, galaxies as we know them couldn't have formed in the time available since the Big Bang. Today, dark matter continues to shape the universe. It forms the gravitational scaffolding along which galaxies are distributed. It determines how galaxy clusters form and evolve. It affects how galaxies merge and interact. Every large-scale structure in the universe exists because of dark matter's gravitational influence. On smaller scales, dark matter fills our own galaxy. The Milky Way sits within a dark matter halo that extends far beyond the visible disk of stars. This halo contains perhaps 10 times more mass than all the stars in the galaxy. As our solar system orbits the galactic center, we're moving through this sea of dark matter. At any given moment, thousands of dark matter particles might be passing through every cubic centimeter of space, though detecting even one of them remains beyond our current capabilities. The invisibility of dark matter is not a limitation of our instruments. It's a fundamental property of the substance itself. We can't see it because it doesn't interact with light in any way. We can't build a better telescope or a more sensitive camera to observe it directly. The only way we know it exists is through its gravitational effects on the things we can see. It reveals itself in the motion of stars, the bending of light, the structure of the cosmic web, and the evolution of the universe itself. Dark matter surrounds us, shapes the cosmos, and yet remains one of the deepest mysteries in science, a reminder that the universe is far stranger and more complex than our everyday experience might suggest. What happens at the edge of a black hole? At the edge of a black hole lies one of the most extreme boundaries in the universe, a point of no return called the event horizon. This invisible surface marks the place where gravity becomes so overwhelmingly powerful that nothing, not even light itself, can escape. Cross this threshold, and you are severed from the rest of the universe forever, drawn inexorably toward the singularity at the center. Understanding what happens at this edge requires thinking about space and time in ways that challenge everything. Our everyday experience tells us about how reality works. Imagine approaching a black hole from a safe distance. At first, it wouldn't look like much, just a region of absolute darkness against the star-filled background of space. But as you drew closer, you would begin to notice something strange happening to the light around you. Stars behind the black hole would appear distorted, their light bent around the black hole's mass in graceful arcs. Some stars would appear in multiple locations simultaneously as their light took different curved paths around the black hole to reach your eyes. This gravitational lensing creates a visual effect, like looking through a cosmic funhouse mirror, with the entire background of space warped and twisted around the dark sphere. The event horizon itself is defined by a specific radius from the center of the black hole, called the Schwarzschild radius. For a black hole with the mass of our Sun, this radius would be about 3 kilometers. For a supermassive black hole, like the one at the center of our galaxy, which contains about 4 million times the Sun's mass, the event horizon stretches millions of kilometers across. The radius grows linearly, with mass double the mass and you double the radius. Despite these varying sizes, the fundamental nature of the event horizon remains the same. It's the mathematical surface where the escape velocity equals the speed of light. Think about what escape velocity means. On Earth, you need to throw something upward at about 25,000 miles per hour for it to escape the planet's gravity and never fall back down. Get closer to a massive object and the escape velocity increases. At the event horizon of a black hole, the escape velocity reaches 186,282 miles per second. The speed of light. Since nothing can travel faster than light, nothing that crosses the event horizon can ever escape. But here's where things become truly strange. Time itself behaves differently near a black hole's edge. According to Einstein's general relativity, Gravity doesn't just bend space, it warps time as well. The stronger the gravity, the slower time passes relative to an observer far away from the gravitational source. Near the event horizon, this time dilation becomes extreme. Picture two observers, one hovering safely far from the black hole, another descending toward the event horizon. The descending observer checks their watch, and everything seems normal to them. Time passes at its usual rate from their perspective. They breathe normally, their heart beats regularly, they think their thoughts at the normal pace. But to the distant observer watching through a powerful telescope, something bizarre is happening. The descending person appears to be moving slower and slower. Their movements become sluggish. Their signals take longer and longer to arrive, and as they approach the event horizon, they appear to nearly freeze in place. This isn't an optical illusion or a trick of perception. Time genuinely runs slower in stronger gravitational fields. As the descending observer approaches the event horizon, each second they experience corresponds to longer and longer periods for the distant observer. At the exact moment they cross the event horizon, from the distant observer's perspective, time for them appears to stop completely. They would appear frozen at the edge, never quite crossing over, their image becoming increasingly redshifted and dim, eventually fading from view entirely. But from the perspective of the person crossing the event horizon, nothing special happens at that precise moment. There's no wall, no barrier, no sensation of crossing a threshold. They would pass through the event horizon and continue falling inward, still experiencing time normally from their own reference frame. This is one of the most counterintuitive aspects of black holes. The event horizon is only special to outside observers. To someone crossing it, the moment passes without any local indication that anything significant has occurred. However, there is something that would become increasingly noticeable as you approached and crossed the event horizon: tidal forces. These arise because gravity weakens with distance, and different parts of your body would be at different distances from the black hole's center. If you fell feet first toward the black hole, your feet would experience stronger gravity than your head. This difference in gravitational pull creates a stretching force. For a stellar mass black hole, these tidal forces become extreme well before you reach the event horizon. The difference in gravitational pull between your head and feet would stretch you vertically while simultaneously squeezing you horizontally, a process astrophysicists have termed spaghettification. Long before reaching the event horizon, the tidal forces would overcome the molecular bonds holding your body together, stretching you into a thin stream of atoms. This would be an absolutely fatal experience occurring far from the event horizon itself. For supermassive black holes, the situation is different. Because they're so much larger, the tidal forces at the event horizon are actually quite mild. You could cross the event horizon of a supermassive black hole, and for a while at least, experience no unusual forces at all. The spaghettification would come later, as you continued falling inward toward the singularity where tidal forces eventually become infinite, regardless of the black hole's size. The event horizon is also where the nature of space and time exchange roles, in a sense. Outside the event horizon, you can choose your direction in space. You can go left or right, up or down, toward or away from the black hole. Time, on the other hand, only flows in one direction, forward. But once you cross the event horizon, this changes. Moving inward toward the singularity becomes as inevitable as moving forward in time is outside the black hole. Just as you can't choose to move backward in time in normal space, you can't choose to move away from the singularity once inside the event horizon. All possible paths through space-time, every trajectory you could take, lead inward. Light behaves strangely at the event horizon as well. Just outside the horizon exists a region called the photon sphere, where light can orbit the black hole in unstable circular paths. Photons at exactly this radius, moving in exactly the right direction, will circle the black hole indefinitely. though any tiny perturbation will cause them to either spiral inward or escape outward. If you could somehow position yourself at the photon sphere and look sideways, you might theoretically see the back of your own head as light from you travelled around the black hole and returned. At the event horizon itself, photons can move along the surface, neither escaping nor falling inward, but this is an unstable equilibrium. Any photon aimed even slightly inward will fall toward the singularity. Any photon aimed even fractionally outward will escape to infinity, though heavily redshifted by the time it reaches distant observers. The effects of gravitational redshift become extreme near the event horizon. Light climbing out of a deep gravitational well loses energy, shifting toward longer wavelengths, toward the red end of the spectrum and beyond into infrared and radio waves. A flashlight shining from near the event horizon would appear dimmer and redder to a distant observer. Right at the event horizon, light is redshifted infinitely, meaning the energy of any photon trying to escape becomes zero. This is another way of understanding why nothing can escape. Even light, trying to leave the event horizon, has all its energy drained away by the gravitational field. Black holes can rotate, and rotation adds another layer of complexity to the event horizon. A rotating black hole drags space-time around with it in a process called frame dragging. Close to the black hole, space itself is being pulled around in the direction of rotation. There's a region called the ergosphere outside the event horizon, where this frame dragging is so strong that nothing can remain stationary. Everything must rotate with the black hole, even if it has enough energy to eventually escape. For a rotating black hole, the event horizon is actually smaller than it would be for a non-rotating black hole of the same mass, and it's oblate rather than perfectly spherical, bulging slightly at the equator. At the poles, you could get closer to the singularity before crossing the point of no return than you could at the equator. The material falling into a black hole doesn't simply disappear the moment it crosses the event horizon. Before crossing, matter often forms an accretion disk, a swirling disk of gas, dust and plasma spiraling inward. Friction in this disk heats the material to tremendous temperatures, often millions of degrees, causing it to radiate intense X-rays and other radiation. This radiation comes from outside the event horizon and can escape, making accreting black holes among the brightest objects in the universe, even though the black hole itself emits nothing. As material in the accretion disk spirals closer to the event horizon, it accelerates to tremendous velocities, often reaching significant fractions of the speed of light. The innermost stable circular orbit, the closest distance where material can orbit without inevitably falling in, lies just outside the event horizon. Material at this radius whips around the black hole in fractions of a second, subjected to intense tidal forces and heated to extreme temperatures before making its final plunge across the event horizon. At the quantum level, something remarkable happens right at the event horizon. Stephen Hawking predicted that quantum effects near the event horizon would cause black holes to emit radiation, now called Hawking radiation. Virtual particle pairs constantly pop into existence throughout space, normally annihilating each other almost immediately. But at the event horizon, one particle of the pair can fall into the black hole, while the other escapes. To a distant observer, the black hole appears to be emitting radiation with a temperature inversely proportional to its mass. For stellar mass black holes, this temperature is incredibly tiny, far colder than the cosmic microwave background, so the effect is purely theoretical at present. But over unimaginably long timescales, Hawking radiation would cause black holes to slowly evaporate. The event horizon represents one of the most profound boundaries in physics, a one-way membrane in space-time itself. It's a place where our intuitions about time, space, and causality break down, where the fabric of reality becomes so warped that the normal rules no longer apply. Everything that crosses this boundary is lost to the outside universe forever, adding to the black hole's mass and slightly expanding its event horizon, while the information about what fell in appears to be lost forever, creating paradoxes that physicists still struggle to resolve. The edge of a black hole is truly an edge, not just of a physical object, but of our ability to observe, to know, and to understand the universe. What comets are really made of. Comets have captivated human imagination for millennia, appearing in the sky as ghostly visitors with long tails that stretch across the heavens. Ancient civilizations often viewed them as omens or messengers from the gods. But these cosmic wanderers are not supernatural phenomena. They're physical objects composed of specific materials that reveal the history of the solar system's formation. Understanding what comets are made of means understanding some of the most pristine, unchanged matter left over from the birth of our planetary system billions of years ago. The core of every comet is its nucleus, a solid chunk of ice and rock that can range from a few hundred meters to tens of kilometers across. In 1950, astronomer Fred Whipple proposed what became known as the dirty snowball model of comets, suggesting that comet nuclei were mixtures of ice and dust. This model has proven remarkably accurate, though modern observations have revealed that comets might be better described as icy dirt balls. They contain more rock and dust than Whipple initially thought, sometimes with dust making up 50% or more of their mass. The ice in a comet is primarily water ice, frozen solid at the incredibly cold temperatures found in the outer solar system. But comets contain more than just frozen water. They also harbour other volatile compounds, substances that evaporate at relatively low temperatures. Carbon monoxide ice exists in comet nuclei, freezing at temperatures even lower than water. Carbon dioxide, frozen into dry ice, is abundant in many comets. Methane, ammonia, formaldehyde, methanol, and hydrogen cyanide have all been detected in comets, creating a chemical inventory that reads like an exotic mixture of the simplest molecules that carbon, nitrogen, and oxygen can form when combined with hydrogen. These volatile compounds exist as ices throughout the comet's interior when it's far from the sun, creating a porous, fluffy structure rather like hard frozen snow. The density of comet nuclei is remarkably low, typically less than water, around 0.6 grams per cubic centimetre. This low density reveals that comets are not solid blocks of ice, but rather loosely consolidated collections of icy particles with substantial void space between them. Picture a pile of snowballs loosely stuck together rather than a single solid block of ice, and you have a reasonable mental image of a comet's internal structure. Mixed throughout this icy matrix are dust particles, tiny grains of rock and organic material. These dust grains are incredibly small, typically measured in micrometers, smaller than the width of a human hair. They're composed of silicates similar to the minerals found in Earth's rocks, compounds of silicon and oxygen mixed with elements like magnesium and iron. Some grains are pure carbon, forming soot-like particles. Others are complex mixtures of organic molecules, carbon-based compounds that include some of the building blocks of life. The organic material in comets is particularly fascinating. When spacecraft have analysed comets up close, or when laboratories have examined samples collected from comet tails, they've found complex organic molecules, including amino acids, the building blocks of proteins, and nucleobases, components of DNA and RNA. These molecules don't indicate that comets harbour life, but they demonstrate that the chemical precursors necessary for life can form naturally in space and were present in the early solar system. Some scientists have proposed that comets bombarding the early Earth might have delivered substantial quantities of organic molecules and water, potentially contributing to the origins of life on our planet. The European Space Agency's Rosetta mission, which orbited and studied comet 67P/Churyumov-Gerasimenko from 2014 to 2016 provided unprecedented detail about comet composition. The Philae lander, which touched down on the comet's surface, detected 16 organic compounds as the comet's warmth released them from the ice. Among these were 4 compounds never before detected on a comet, including molecules that can act as precursors to amino acids. The comet's surface appeared darker than coal, with a reflectivity of only about 6%, due to the dark organic compounds mixed with the ice. When a comet approaches the Sun, solar heating begins to affect its structure. At distances beyond about 5 astronomical units, 5 times the Earth-Sun distance, roughly Jupiter's orbit, a comet remains frozen and inert. But as it moves closer, sunlight warms the surface. The most volatile ices, like carbon monoxide and carbon dioxide, begin to sublimate, transforming directly from solid to gas without passing through a liquid phase. This sublimation creates pressure beneath the surface, and when that pressure becomes strong enough, gas bursts through the surface, carrying dust particles along with it. These jets of gas and dust create the coma, the glowing atmosphere that surrounds the nucleus and makes the comet visible from Earth. The coma can grow to enormous sizes, sometimes exceeding the diameter of Jupiter, even though the nucleus producing it might be only a few kilometers across. The gas molecules in the coma, particularly water vapor, are broken apart by solar ultraviolet radiation, creating a complex chemistry. Hydroxyl radicals, hydrogen atoms, oxygen atoms, and other fragments fluoresce in sunlight, emitting light at specific wavelengths that give the coma its greenish or bluish tint. The dust released from the comet creates a dust tail, pushed away from the Sun by radiation pressure, the physical push that photons exert when they strike and reflect off particles. This dust tail typically appears yellowish-white because it's sunlight reflecting off dust particles. The tail can extend for millions of miles, creating the spectacular displays visible from Earth. A separate ion tail, composed of ionized gas molecules, is pushed by the solar wind rather than radiation pressure. The ion tail glows with its own light as the ionized molecules fluoresce, often appearing blue due to emissions from ionized carbon monoxide. This ion tail points directly away from the Sun, shaped by the magnetic fields carried in the solar wind. The nucleus itself undergoes changes as the comet repeatedly approaches the Sun. Each passage evaporates a layer of ice from the surface, typically removing a few meters of material per orbit for comets that pass close to the Sun. As the ice sublimates, some dust particles escape with the gas, but others fall back to the surface, gradually building up a layer of dust and larger rock fragments. Over many orbits, this can create a crust of non-volatile material covering the underlying ice, insulating it from solar heating. Some old comets develop such thick crusts that they become inactive, no longer producing visible comas or tails, even when they approach the Sun. NASA's Deep Impact mission in 2005 deliberately crashed a copper impactor into Comet Tempel 1 to excavate beneath the surface and observe the fresh material. The impact created a crater and ejected plumes of material that spectroscopic analysis revealed to be rich in water ice mixed with organic compounds and fine dust. The material beneath the surface appeared similar to, but slightly richer in ice than the surface material, confirming that the interior retains more pristine composition while the surface becomes processed by solar heating. The ratio of different isotopes in comet materials provides clues about where and when they formed. Deuterium, a heavy isotope of hydrogen with an extra neutron, exists in different ratios to normal hydrogen depending on the temperature at which water formed. Measurements of the deuterium to hydrogen ratio in various comets have shown considerable variation, suggesting that comets formed in different regions of the early solar system or at different times. Some comets have deuterium ratios similar to Earth's oceans, while others differ substantially, helping scientists understand whether comets could have delivered Earth's water. The dust particles in comets are themselves diverse and complex. Some grains are crystalline, showing that they formed at high temperatures, possibly near the young sun, then were transported outward and incorporated into comets forming in the cold outer solar system. Other grains are amorphous, formed at low temperatures in the outer reaches. This mixture indicates that the solar nebula was not a static, orderly system, but rather a dynamic environment with extensive mixing, where materials formed in the hot inner regions could be transported outward and vice versa. Comets also contain tiny pre-solar grains, particles that formed around other stars before the Sun existed and survived incorporation into our solar system. These grains have isotopic compositions distinctly different from solar system materials, marking them as true interstellar visitors preserved within comets. They're typically only nanometers to micrometers in size, but they're extraordinarily valuable because they provide samples of stars that lived and died before our solar system formed, preserved in these frozen time capsules. When comets break apart, as they sometimes do when tidal forces or internal pressure cause the nucleus to fragment, the exposed interior shows the layered structure built up over billions of years. Some regions are richer in ice, others in dust. Some layers contain different mixtures of volatile compounds. These variations likely reflect changes in conditions in the solar nebula as the comet grew by accumulation, recording the changing composition of material in the comet-forming region over time. The darkening of comet surfaces producing the surprisingly low reflectivity observed by Rosetta and other missions results from the organic compounds being altered by solar radiation and cosmic rays. This radiation processing, called space weathering, gradually darkens and reddens the surface materials over time. The very dark surfaces of comet nuclei tell us they've been exposed to space for long periods, accumulating radiation damage that has transformed the original icy material into a darker, more complex mixture. Comets are messengers from the outer solar system, preserving materials that have remained largely unchanged for over 4 billion years. While planets have been geologically active, melting and reforming their materials countless times, and asteroids have been heated and altered, comets have remained frozen in the deep cold of the outer solar system, maintaining their original composition. They're samples of the primordial solar nebula, the disk of gas and dust from which the planets formed, carrying within their icy matrices the water, organic molecules, and mineral grains that were present at the dawn of the planetary system, offering glimpses into the raw materials from which everything in our solar system, including Earth and ultimately life itself, was constructed.